All right, good morning, everybody. My name's Sam Burden, and it's my pleasure to host Dr. Will Nothwang visiting us from Army Research Lab. I've known Will for quite a while. Originally met him when I was a PhD student back in grad school, and he was kind of a mentor for me on a grant that I was contributing to that he was kind of a lead on. And then more recently, we've been co-mentoring a postdoc split between ARL and UW, and so now he's kind of turned into more of a colleague and co-mentor with me. So Will earned his PhD from Clemson University in material science and engineering. And after that, he started as a postdoc and has since moved up to being a team leader in the electronics for sense and control team within the Sensors and Electron Devices Directorate in the Army Research Lab. He has research interests that span a lot of different areas. So you see, he started out doing solid-state physics, and then what he's going to talk about today is kind of human neurophysiological monitoring and estimation and prediction. And so his research interests really span like what DoD calls position, navigation, and timing. So you can think of this as like devices that measure and provide useful information, and all the way up to integrating those into micro-autonomous vehicles on the MAST project, which is a project I worked on him with, all the way up to trying to sense and integrate humans into decision-making processes. He's currently the PI for the Privileged Sensing Framework, which is largely what he'll talk about today. That's part of the Autonomous Research Pilot Initiative in DoD. And the Microelectronics Center of this Microautonomous Systems Technology Collaborative Technology Alliance, which is the thing I was a part of as a grad student. He has a number of commendations from the Army, and one of the more significant ones recently is he contributed to a team that won the ARL Director's Choice Award for Innovation. So with that, I'd like to give Will a very warm welcome.
Thank you very much. Thank you. All right, thank you for that introduction, Sam. I will try and live up to that. And most of those words and titles and all of that, most of you probably aren't that familiar with Army Research Lab, and so I'll try and talk a little bit about what the Army Research Lab is and all the stuff that I talk about. But first thing I'd like to talk about this morning is why I'm here. So in addition to Sam inviting me and Ryan telling me such glowing things about the stuff here, the reason I'm here at University of Washington is pretty straightforward. And that's when you go outside these doors and you go off campus and you start to deal with the real world problems that are out there. They're multidisciplinary, multicultural, diverse problems that require a multidisciplinary, diverse, multicultural group of people to solve those problems. And I get a chance to go to a lot of different universities and talk about my work and collaborate with a lot of different professors. And I don't want to say University of Washington is unique, but you guys get it. This collaborative technology space and actually solving these problems as a group, this is something that's not hard for you. You guys don't have to try for this. And so this is the reason that I'm here, is because I need people like you guys to come work with me to solve the problems. So I'm going to tell you a little bit about what those problems are, and I'm going to ask for your input. And I don't want this to be me telling you and me speaking to you for the next 50 minutes. I'd really like this to be a dialogue, because if you make me go through all these slides, I'm going to be really miffed. So please, stop me, ask questions, anything that you want, and I'm more than happy to not get through most of these slides. So with that, I'd just, like to talk a little bit about what the Army Research Lab is. I'll talk more about it towards the end, and those are more than happy to leave those slides off if we don't get to them. But what is the Army Research Lab? So we're the premier research laboratory for the land warrior, which is lots of words, but I'll start with what we are not. So we are not a funding agency. So we don't give money to academics. Sorry. We are a honest-to-goodness research laboratory. We are the corporate research laboratory for the Army and the Marines, which means that we do that full gamut of research necessary to provide the basic science all the way through transition science to the field for the land warrior. And that covers a huge gamut, a huge spectrum of different opportunities. And I'll talk about a little bit about that. So we have a brand new ARL director within the past couple of weeks, and he's always hammering us on this last bit. So we're charged with discovering, innovating, and transitioning. So what that means is that we don't just do basic science and publish papers. We don't just do innovation and generate patents. We do all of that stuff, and we get held accountable for all that stuff. But we are ultimately responsible for making sure that it gets out to people to use it. So I had an academic colleague recently that was suggesting that one of his students come work for me as a postdoc. And this is how he put it. This is what our job is to, in the real world, make sure that the technology works. He used a little bit more colorful language, but that's what our job is. So we work a lot with academics. And you guys do the proof of concept, And then we take that proof of concept and we take it into our lab and we break it and we find all the different ways it breaks and we figure out how to fix it and make it work in the real world. So that's what our job is. And that's what we do at the Army Research Laboratory. So my team, Sam mentioned I'm a team leader. So this is like a project lead, for lack of a better term. I'm not a manager. I don't have any kind of role in that regard. But what I do is I lead and design projects and I lead projects. And so what you see here is my team. So there's lots of different color codings and all of this, but what I'd like to highlight is that the ones at the top in black, those are the government employees. So there's only 4 of us on this team. And there's 14 other people that work on the team, and those are a collection of postdocs and students coming from academic colleagues and people doing sabbaticals and contractors all coming into my office, into our labs to work. So it's a very fluid environment and a very welcoming environment for lots of different people to come and work with us. Additionally, we have responsibilities that I show here at the bottom, which is we're responsible for getting our product, our innovations, our research out of the lab. And sometimes that is, direct translate from us to some program manager in the Army, but most often it's not. Most often, so the Army doesn't make anything. I don't know if you guys realize this. We don't build or make anything. We buy products from the commercial industry to fill out whatever the orders are. So which means we have to take our technology from the lab and actually put it out into the commercial space for other people to make it better and robust and commercially viable products. So one of the ways we do this is through SBIRs and STTRs, and so we seed a lot of the ideas that we develop into these products. I'm not going to talk a lot about the stuff on the right, but those are ultimately who our customers are. Those are who pay our bills. All right. So within my team, we do research across all of these different application spaces. Sam said at the beginning, it's a very diverse application space. Everything from the position navigation and timing, so how do we do precision measurement in highly contested environments? So this is a unique trade space that we in the Army have to deal with. We don't have access to GPS. Just full stop, we don't have access to GPS. Not only do we not have access to GPS, we actually have lots of people that are trying to screw up our navigation capabilities. So under those environments, how do we actually make good state estimates of where we are in the world? So this is one of our core research areas. Taking that and focusing it specifically on autonomous systems, how do we do that on very small scale autonomous systems with small lightweight computers and sensors that will actually fit on a small scale autonomous system? So this is the second area of research that we do. Generally speaking, today I'm not going to talk about those. I'd be more than happy to talk to you ad nauseum on those topics if you would like. But what I'm going to talk to you today about is the third area, which is how do we actually take the human and pull them inside the design loop? Generally speaking, in a control methodology for almost every autonomous system that I can think of that is deployed. Well, actually, let me start there. So how many of you can think of an autonomous system that is actually in the commercial market or DoD market? Yeah, Christy. Yeah, there's lots of quadrotors, but how much autonomy is on them?
Oh, yeah.
Yeah. So there's a big challenge right there. So we have there's decades of really good people doing really good work on autonomy. And right now it's generated, maybe a handful of technologies that have actually, if we're being generous in how we count that. And there's a lot of technological as well as policy challenges for how we do that. So I'm going to not really get into that, but one of the big challenges is right now we require the human to be the pinnacle of any decision-making loop involving an autonomous agent. That may or may not be a good decision. So how many of us already this morning have made mistakes? Errors. How many of you had a test so far today? Yeah, exactly. We're not infallible. So asking us to be the ultimate arbiter of any decision is probably not the best way of going forward. Not that autonomies are perfect. They have their own issues. But if we can actually pull the human into the design loop, into the control loop, we can perhaps take advantage of what autonomies can do as well as humans and make our decision-making process much more robust and resilient. So that's what I'm going to talk about today. So just a general introduction. So those are the 3 areas. I'm going to briefly mention the first 2, but then focus on that third area. I'll give you an overview of ARL, but I would like to really mention that this is a blatant sales pitch. I want you guys, to come work with us. So those can take a variety of different routes. So we take summer students, we take co-ops, we take everybody from BS level all the way up to PhDs and postdocs, sabbaticals. We have open opportunities for people with sabbaticals. But more importantly, we have what we would call an open campus, which means we have fantastic world-class facilities, and we would love for you guys to come and work with us on those facilities. We would love for you guys to come work with us on ideas that are important for both of us. So I will continue to reiterate this. This is a blatant sales pitch to get you guys to come work with us on some really cool problems and use some cool equipment and hopefully generate some great ideas and great papers and great things at the end of the day. All right, so this is a kind of a catalog of all the different projects that I work on, which is, I'm not going to go into them or even bore you with the details, but I'd just like to highlight they range from things up here at the top, like this precision measurements, and this LLRDP project to the CMSC FAT at the bottom. So these are big projects. Think like 3 MURIs put together. So 40 PIs working on this project, to single investigator projects like this one right here. So that spans the whole gamut of projects in my team. And I'll talk a little bit about some of those, but the big thing that we have, big kind of phase change at the Army Research Laboratory recently is we've really embraced this idea of big science. So this is something that used to be the purview of DOE and NASA. And the Army has really started to take, we're looking at these big, wholehearted problems and taking the end-to-end approach on how to solve them. All right, so precision measurements for contested environments. I already mentioned part of what we do, but basically what this is how do we make better state estimates from crummy data? So if you think about your cell phone, you have a 6-axis gyro, you have a 6-axis accel in there, maybe a 9-axis gyro and accel in there, but it's pretty crummy data. The drift in those is on the order of tens of degrees an hour if you're lucky. So we need, sub-hundredths of a degree per hour to actually have a navigation grade quality system. But what we do have access to is that commercial electronics industry. So how can we take advantage of all those products that are being developed for your cell phones and for your cars and for everything else? Because let's be honest, the DoD is no longer even in the electronics industry. We don't influence the electronics industry at all. So if we want to use electronics in our systems, we have to leverage what's already being developed and maybe add a little bit of secret sauce at the end. So this is this is the approach that we're taking is, can we take all of those commercial sensors that are available, those commercial computational structures, and use them with some secret algorithmic sauce to make better state estimates. And that's what we're doing here. In addition, we have some novel gyroscope designs, novel accelerometers, and novel sensor designs and all of that. But most of what we're doing here is, can we leverage what's going on in the environment to make better state estimates? And that's really all I'm going to say on that. Excuse me. In the area of autonomous systems, this is taking that to the next level, and what I'd like to highlight here, and it's probably best done on the next slide. Hold on just a second. Start my timer. When we started working in this space many, many years ago, one of the big challenges is when you want to do GPS-denied state estimation, you want to do algorithms that tell you how good you're doing in the world. And you want to do it outside of Vicon, because let's be honest, you can't take a Vicon system out into the real world to actually get state estimates. So one of the big challenges is, in order to figure out how good you're doing, we don't have data sets out there with ground truth data to let us figure out how our algorithms are doing. So one of the big things that we're doing in our group is generating those data sets. Full end-to-end, high-fidelity, multi-sensor data sets. So this is what we show right here is, this is what we refer to as our sensor kebab, which is any number of different sensors in a plug-and-play fashion we can put onto this kebab with any computational structure to collect the data and run it through a variety of different environments. So you see all these nice, pretty pictures across the top, and these are fantastic scenery, and every single one of them in a unique way will break a state estimation algorithm. So how do we collect ground truth data in that so that we can then really try and solve this state estimation problem? So that's one of the things we're doing. And we've started to make some of those data sets public, and over the next year or two, we're going to actually put these data sets out there for very smart people out there to solve this problem for us. So we're more than happy to have intelligent people out there and leverage other work that's going on. We don't need to be the sole arbiter of these good ideas. All right, so that's all I'm going to really say about those two application spaces. If you have questions, you want to know more about what we're doing, I have many, many, many different slides on those application spaces, and I can talk to you guys afterwards about that. What I'd like to talk to you now about is human sense and control. So pulling the human inside the control loop. So what we're talking, and there's a number of different projects in this space, but I've already kind of introduced it. How do we pull the human inside of the control loop? When you start to think about what that really means, what that implies is that we have to treat the human as we would any other sensor or computational structure in a control loop, which means we need to have a state estimate for that human, which is a non-trivial thing. So how do we use sensors, wearable sensors, so everything from your Fitbit to an EEG, to come up with viable state estimates of what's going on in a human. So when I say state estimate, it's easy to understand when we're talking about an autonomous system. That's your 6-DOF pose or your velocities or something like that, or where you are in the world. We can wrap our mind around that. When I talk about state estimates for the human being, you have all of that stuff, plus you have, are we tired? Are we paying attention? Are we thinking about something else? Are we surprised? Did we just see something of interest? All these other things that are going on inside of us that are less easy to access and measure, but are just, or if not more important, to influence how that decision-making state estimate is coming off the human. Furthermore, these are abstract concepts, so when I say you're surprised, can you give me a quantitative measure of what I mean when I say surprised and how I measure that? So if you look at the literature in the human-robot interface world or even the human subjects world, there are infinite number of quantitative estimates of how you do this. So what we're trying to do is systematically develop the mathematical formulations for including the human in the decision loop, including these state estimates. So I'll go through some of the details of this, and there's a number of different projects that I highlight down here at the bottom that influence this. Some of these are developing novel wearable sensors, and some of them are the actual mathematics. What I'm going to talk about are these two at the very bottom. So the privileged sensing framework, and then what is nice and easy to remember, CMS-CFAT, and I'll tell you what that means in a second. But those are the two projects I'm going to focus on, and I'll mention some of the others. But please stop me, ask questions, because if you make me go through all these slides. All right, so privileged sensing framework. This is something that has been funded by the Secretary of Defense's office, and it is a project to define what is the fundamental mathematics that incorporate human with autonomous systems. So if you go to the literature in human subject research and you go to the literature in autonomous systems research, and you'll see that there's fantastic modeling that goes on in both of them. There's great mathematics that go on in both of them, and they're completely and totally disparate. So how do you actually combine the two in a meaningful way? And I'll talk a little bit about what I mean by that. But this is the fundamental challenge of actually pulling the human into the loop, is making sure you have a common mathematical framework. Once you have the common mathematical framework, then you can do something with it. But at this point, we're just kind of coming up with heuristics, which is not a long-term solution. First of all, I'd like to mention the people that I work with on this project. So as Sam mentioned, I'm the PI, which means I don't do anything. These are the people that actually do all the work. They cover everything from a few academics at Columbia to lots of other researchers at other government labs. So I think we cover most of the major government labs and have a couple academic collaborators and a couple of contract personnel as well. All right, so when I talk about the mathematics, there are three pillars that I'm generally referring to: confidence, consequence, and multi-scale integration. So consequence sounds exactly like what it means. When you make a decision, humans in general, we take into account what is the consequence of that decision. What is the long-term impact when I make a decision on my further interactions with that other person, my further long-term financial impact of that decision? We generally do this. We don't necessarily do it well, but we at least take that into account. It's part of our internal decision loop. There wouldn't be a lottery system. There wouldn't be a lot of other these things that if we did it well. But we take consequence into account. Autonomous systems, full stop, do not do this. The only way autonomous systems do this is if a human codes a cost function and puts it into an autonomous system, which means that they don't have any ability to really independently reason about how their interactions are influencing anything else around them or in time. And this is a fundamental limitation of integrating an autonomous system with a human, is this disparity. On the other hand, we have the issue of confidence. And this, likewise, is exactly what it sounds like. This is the statistical confidence you have in your ability to make an estimate. We do this very, very well for hard systems like autonomous systems, sensors, computational structures. We know the statistics of those systems. We can do that. We can do that very, very well. For human systems, that's a lot harder question. This is a really, really highly multidimensional confidence estimate. And buried in that is the subtlety of when I say the word confidence. This is not just the statistical confidence I have in Ryan writing that paper. It is the trust that I have in Ryan to do that. And that subtlety is very, very important for humans and is not necessarily involved in how we currently manage confidence. The final area is multi-scale integration. And so this, when you have information coming into a system, that information is going to come across multiple different timescales. You're going to have things that vary at the nanosecond level to things that vary at the year level. So how do you incorporate variations on that time scale? There are spatial variations in that time. There are environmental variations in that time. So this is a highly non-linear integration problem of how do you do this. And we don't really have a good handle of how we do that. So this is the third leg of that pillar. All right. So we can't solve that entire problem space in this one project. But what we can do is get started and have some proof concepts that we think can generalize to a lot more solutions. And this is what we've tried to do. So we've generated some interesting ways of estimating consequence, and I'll talk a little bit about those. And part of that is how we integrate a priori information. So this can take a lot of different forms, and there's a lot of literature. So we're not the first people to work in this space. Absolutely not. There's lots and lots of other people that have gone and done really good work before us. So how do we take those bits of data that have been generated before, whether those are heuristic relationships or general large bodies of data, how do we take that a priori information and use that and influence what we're doing here? So that's part of this specific aim. In the second specific aim, we have developed new novel methods of statistically quantifying human behavior, human inference, human state. And I'm not going to get into the hardcore math of what we did here. I'm more than willing to talk to you afterwards if you want to, but I'm going to talk more about the consequences of those confidence estimates. And finally, in the large one, we took this multi-scale information and integrated it into two relevant demonstration experiments. And how do you deal with multiple humans and multiple AI systems trying to do target identification? So think you have a massive database of information and you want to correctly catalog everything into one of many bins. And you have at your disposal a lot of different resources, but you don't have infinite resources. So you have a number of different AI agents and you have a number of different humans, and this is the giant queuing problem of how do you choose who to solve this problem, given a finite amount of limited resources and an infinite amount of data that needs to be solved. And then the other one is if you have multiple humans and multiple robots trying to do a state estimation problem like exploration or target tracking in ID. So I'll talk a little bit about those. All right, so I largely already talked about this. So this project is coming to an end in this September, and it will transition into an internal research project, which I'll mention in a second. All right, so these are kind of the big core questions within this project, and I'm just going to talk about these, the trust and autonomy issues, and then the target ID and robot navigation pieces. So I'm happy to talk about the other ones, but there's not enough time to really get into depth on all of those. All right. So in convoy operations, the military as well as a lot of commercial industry is moving towards human-assisted convoy operations, which this means is basically you have one or two humans to drive a whole bunch of trucks because it's a lot more cost beneficial. So that reduces risk, it reduces cost, it reduces lots of other things. There's lots of reasons to do this. There's lots of challenges in doing it. The fundamental one that you have is when does the human take control and when does the autonomy take control, and how do you determine who should be in charge at what time? Which is a very, very hard problem, and lots of people have looked at that. So what we have done as part of this research question is we have facilities at our TARDEC. So that's the Tank Automotive Research Development and Engineering Command, which is outside of Detroit. And they have this 6-DOF motion platform that mimics the inside of a crew cab for an Army vehicle. And it's a 180-degree by about 60-degree simulation environment. So we can create that simulation environment and have them drive with an autonomy through this new environment that we create for them. We have them do a lot of different things that a human in this environment is going to have to do, like not hit pedestrians, stay on the road, stay with the vehicle in front of you. Things that sound pretty straightforward, but are really not. I mean, most of you that have driven through Seattle realize that, just by yourself, this is a challenge, not having to manage 10 other vehicles in the convoy. So you're going to have those same challenges out in the real world with an autonomous system. So we put them in this environment, and we have them fully kitted with physiological measurement techniques, tools, to try and figure out what is their state, how good are they doing right now. We also have an estimate of what's the risk environment outside of that crew cab. So we can estimate what are the environmental influences. So what you see here on the lower left is basically what you would like to generate for each of these environments, which is a trust matrix When are you over-trusting, when are you under-trusting, when are you overestimating your own capabilities? So these are up here are very abstract, but you'd like to come up with a high-fidelity quantitative estimate of who should be in charge when, and if you're actually engaging in autonomy when that happens. So that's what's shown here, and I can get into specific examples later. And once you have that, you have a decision tree. So what I show here is a Bayesian decision tree. We actually use a modified Dimster-Schaefer decision tree, but it's basically the same type of thing. So you have a whole bunch of environmental factors here at the bottom, at the top. You have a whole bunch of physiological factors there at the bottom that tell you how good the human is doing right now, how good the autonomy is doing right now, and who should be in charge. So those are the three fundamental estimates that you have to make. And then if the human is in charge, but the autonomy should be, how do you actually actuate a human? Yeah, exactly. So in a control loop, you have to be able to actuate the system. Otherwise, it's just a state estimation problem. So how do you actuate a human? And there's a lot of work that goes into how do you influence a human. Yep?
You said the weights on that Markov model, is that something that you did it by hand, or is there like some reasoning behind those?
Oh, there's lots and lots of reasoning and machine learning and different, lots of machine learning that went into those different models. So that's a great question, and it's a segue to the bigger question, which is trust. So what we're trying to do is manage trust. So one of my colleagues at ARL just published a review paper on trust and autonomy. And what she found when she looked at the literature in trust and autonomy is there are over 300 working definitions of what trust means when just that trust and autonomy community. So actually coming up with what is a quantitative definition of trust is probably not informative. So what we have done is take a step back and say we're really not all that concerned about trust per se. We're much more concerned about performance. So we want the overall system performance to be as good as possible. I hedge using the word optimum, but in controls that they like that word, but as good as possible. So what we did is we did a huge number of experiments, human in the loop, to estimate. So this series of experiments was done in two parts. The first part is the human driving with a variety of different autonomies, and I'll talk to you about the results. And we took all the physiological and all the environmental data, and then we did a huge amount of machine learning on that to come up with these weights of who should be when, how, all that kind of stuff. Then we did the second series of experiments, which we actually then try and close the loop. So it's no longer just a state estimation problem, but we integrated actual actuation mechanisms with the human, and so those trials are currently ongoing right now at TARDEC. And we're hoping, knock wood, that it'll actually show that it's a much more viable paradigm. So let me get into what I mean by that. So this is generally what I'm talking about. So this is your racetrack, if you will. And there's a variety of different features along this racetrack. What you see here is, depending on how good the autonomy is, how good the human is, and the general overall trust and autonomy, the human is going to have a different performance across that race course. And that's really all I want to show. I'd like to, there's some temporal dependencies on these trusts. So one of the things that we know from experience with autonomy is it's really, really easy to drive trust off a cliff. I can dramatically impact, in a negative way, your trust in any autonomous system. What is much more difficult is to modulate that trust by little bits up or little bits down, and we don't really know how to do that. So that's what we're trying to get here is can we just a little bit up or a little bit down to get you into the appropriate level of usage, instead of trust, usage of that autonomous system. So what you see on your left is a highly reliable autonomy, and you see that generally the performance is good. Blue is good, red is bad. And an appropriate usage of that trust, yes?
The tests that you're doing, are these primarily with military personnel, or is it a broad range of?
Yeah, that's a good question. So it's generally, we would love to have had a giant set of military cadets come in and run this, but it's a broad range of human subjects, variety of ages, variety of, both equal measurement of sexes, some military, some professional, some, so it's a very broad range of people that did this. So we are trying to develop this for the military, so it'd be awesome to have a military subject data pool, but that wasn't available. So it's, we put out Craigslist ad to recruit people and stuff like that. So, and we paid them, so they showed up. And we paid them to do well, so they tried to do well. So, all right. What you see on the right is when you have a bad autonomy, people do worse, which is expected. What's interesting, though, is if you look at the data in a little bit more detail, so shown here is, so FG is full good, FB is full bad, so there's 4 different levels of autonomy. So the autonomy was asked to either maintain position in the lane laterally or also longitudinally. So full autonomy means it has both of them, and then speed only, so speed good is only longitudinal control. So think of cruise control in your car versus lane offset in your car. So these are the types of autonomies that we employed. And what you see is that, unfortunately, the usage rate and the violation rate doesn't differ really across those autonomies, which means that people are coming into this with a preset understanding of what they think the autonomy is going to do, and that's how they use it, and they don't necessarily use it well. So this has informed us on how we design the next series of experiments and how we educate, how do we inform people of what the autonomy is capable of. What you see on the right is that, generally speaking, good did better than bad. Shocker. And that full autonomy had a much wider range of subject results as opposed to speed only. So speed only was a much tighter network. Right, so I'm gonna, as we went through, and all these results are statistically significant, and I'm just gonna skip through that. So what you can see, generally, you get some nice clustering of the data. So the full bad is in the lower left, full good is in the lower right, but generally beyond that, there's not much you can say. But what is interesting is that when you look at, generally, we designed the autonomy so that the full good is approximately equal to human performance in this task. So what you would like to see is what that green line shows there. So when somebody is using that autonomy as identified, so when 1 here, that's the ratio of human to autonomy performance. That means they're roughly working the same, and you'd like to see about a 50% usage of the autonomy if that's the case. And what you see is a substantially lower usage of autonomy in those cases, and it generally falls under this curve. So if somebody appropriately trusted the autonomy, it would follow this curve. And what you see is a uniformly lower usage of the autonomy and a uniformly poorer assessment of when they should use it. So this speaks to institutional biases of how we actually want to use autonomy. And this is a much bigger problem within society, and this is one of the reasons that Google is taking such a nice, slow time in deploying their systems. It's not just to make the systems work well, but it's also to make sure that we, as consumers of those systems, understand how to use those systems. All right, so I'm not going to get too much into that. So what we do from that data, and this gets to your question, so what we have is an environmental assessment of who should be in charge and what is the likely risk over the next little bit, and that's what you see in this series of graphs. So this is for the full good autonomy. And when the autonomy is in charge, and as that spike goes up, that means that there's a high likelihood or an increasing likelihood that the autonomy is going to make a mistake over the next window of time, 10 seconds or whatever that window is. And so what you would like to see is that when the spike goes up, that you switch to the other person in control. So you take control back from the autonomy, or when the human's in charge, so both of them are plotted on the same thing. So when this block is at the top, that means the autonomy is in charge. And when the block is at the bottom, that means the human's in charge. So what you would like to see is that as this is going along, and you see a spike in likely risk, that you switch. So this right here is a good switch. That means the human anticipated that the autonomy was going to fail in a certain environment and took control over from the autonomy and maintained situational awareness of the environment well enough so that they could make a clean switch. What you see here in this green highlight is a region where it wasn't such a good switch. Yes?
How does the switch happen, and does the human driver know when they are in control or when
Absolutely.
the
So,
is in control?
Absolutely, that's a good question. So the human has control over who's in charge. And there's a toggle switch for whether they choose to be in charge or whether they choose to have the autonomy in charge. So it's an awful lot like your cruise control on your vehicle. You can turn it on, and you can check out of the cruise control whenever you want. So it's the same type of system. So the human has ultimate control, which gets back to the second question of how, if the human has ultimate control, how do you actuate that human to do what you want? And so that's more of a coercion. So we can't take control away from the human, although we're getting better at that with anti-lock brakes and all this kind of stuff. We're gradually, inch by inch, allowing acceptance of these autonomies. So that's a good question. All right, so I'm not going to spend too much more time on it. What you see for a full bad autonomy is a lot worse performance. And generally speaking, humans making a lot worse decisions about who should be in charge when. So there's incentive within this test paradigm for the human to use the autonomy. So you have lots of pedestrians crossing the road, like maybe next to campus, and you'd really like to not hit the pedestrians. And the task load for not hitting pedestrians is so high that you'd like the autonomy to maintain follow distance to the convoy in front of you when it's appropriate. So there's incentive for them to use the autonomy to maintain that workload, and it's not always done well when the autonomy is bad. Generally speaking, what happens is if the bad autonomy makes a critical mistake, like you hit somebody when the autonomy is in charge, then people just turn the autonomy off and they don't use it again, and that's what we'd like to avoid. All right. Yep.
This analysis seems to sort of look at sort of very hard decisions with regard to autonomous versus manual. Have you made a determination on whether there's value in sort of graded levels of trust and graded level of automation? Yeah. What's your insight on that?
Yeah, absolutely. So yes, absolutely. There is a huge value to graded levels of integration of the human and the autonomy. And I think that the absolute poles, human or, is probably not the paradigm we want to be in. So there's some level of and. And being able to do that, however, means we have to have a good state estimate of the individual agents so that we know how to best utilize them. And so this is the first step towards getting towards that. And what I'll show in a few of the other experiments is where we have much better assessment of those agents, we can make good and decisions. But I agree with you completely, and is probably where we want to be. Yes?
Include software and hardware. Is it possible to build a hardware and software that doesn't make any mistakes?
Oh, sure. If you don't want it to do anything. So, real mechanical systems. Yeah, absolutely. So real mechanical issues are going to have failure modes. That's just, and so you design away from some of those failure modes. There's lots of institutional ways that we, can design to include safety margins. But even with safety.
Humans to figure out what the failure mode is going to be, which is a problem in itself.
Right. Absolutely. So, and that's, there's not going to be a perfect autonomy. There's not going to be a perfect mechanical system or even AI system working on that. Humans aren't perfect either, so understanding failure modes, being able to predict failure modes, and being able to influence. So if you know an autonomy is going to fail in a certain environment, how can we then leverage the human's input as opposed to so that's a big long-term research question of how do you do joint. And so this is one of the reasons that I'm a big champion for pulling the human inside that decision loop. So if you can make an estimate of when the human's doing well and when the autonomy is doing well, you know better how to do that. But yeah, this is, autonomy is not going to be perfect ever. Mechanical systems, we all know, fail. Human systems, we know, fail. So maybe between them all, we can do better. All right, so I'm not going to belabor that graph. All right, so this gets a little bit to what you were talking about, the and question. So in this one, this is an image triage question, and I'm not going to go into a lot of the details, but this is an RSVP paradigm, so rapid serial visual presentation, which means that humans are shown images on the order of 5 to 15 hertz, which is much faster than we can cognitively make a decision or manually make a decision on whether or not we saw something in that image. However, neurologically, those signals are there. And so what we have is a human fitted with the EEG and physiological monitoring systems so that we can sample the human's decision process and be able to make determinations whether or not they saw a target. In parallel, we have a number of different AI agents that are trying to do computer vision estimation, target localization on this. And what we would like to do and what we have done in this example is take those independent agents and fuse them, so a lot like what you're talking about, to see if we can get better with an and as opposed to an or. And what you see, and it's hard to see in this graph, but shown over here on the left, this is a deformable parts model. So outside of deep nets, this is probably the best performing computer vision algorithm that's out there. And what you see is you get on the y-axis, this is area under the curve, or mean average precision. And a deformable parts model does about 0.25. So area under the curve is 1, 0.25 is not a great result, but as far as computer vision literature, this is pretty competitive with the best computer vision literature out there. So this is, let me say a little bit about the the data set that we were looking at. This is a very large office objects data set. So those of you that are familiar with the Pascal VOC data set, that's a commercial data set or open literature data set. So it's a similar complexity to the Pascal VOC type of data set. So what that means is you have a picture of like this lecture hall, and you say, all right, where's the door? And so it's not just a door centered in the frame, but it's a very complex image, and you have to say, all right, there's part of a door way back there, and that means there's a door in that image. So it's that type of image data set. So we turn the computer vision loose on it, we turn the human loose on it, and what you see is that when you fuse all the different computer vision algorithms, and that's what's shown here, you generally get a better fusion performance. And so we have an in-house special fusion algorithm, this modified Dymster-Schaefer, that seems to outperform a lot of the other fusion algorithms that is out there. But what I'd like to also point out is over here on the far right, and that is when you start to add in the human performance. So you take all these neuroclassifiers, you take their button press when they can actually manually indicate that they've seen a target image, and you get a statistically significant 30% increase over computer vision alone. So this is human plus computer vision, and you get a 33% increase in performance. So the next question, or the follow-on question, is how do we, that grand queuing question that I was talking about. We know that humans plus computer vision does better. And now we want to see, can we push the false negatives and the false positives and prefer one or the other? Can we actually classify a giant image database as quickly as we can, as best as we can? And what does it mean when we say quickly and best? So those are the kind of questions that we're following on with this. All right, the next one I'd like to talk about is a little bit more looking at the consequence issue. So if we ask a human to make an interdiction decision, so what I mean by this is you have a target that you're tracking, and we ask you to determine when you want to interdict that target. And we say, all right, shown up here on the upper right, so this is the type of map that you may be given as a commander in that decision. So generally speaking, within the military, you don't have firsthand information on that. So non-line of sight actions mean that you are relying on somebody else to give you information when you want to interdict a target. They give you a coordinate system, they tell you what you're looking for, something like that, and then you have to make the decision based on that second-hand information, sometimes third-hand or fourth-hand information of when and where and how to make that decision. So when we ask humans to make this decision based on inherently flawed information, how it gets to you, how well do they make that information? And can we add an autonomous decision support system to improve how well you make that decision? So this was the question that we went into this. And so this is work that Ryan Robinson has led, and so if you want further information on this, he can give you all the gory details of how it was done. But this is human-in-the-loop decision-making, asking them to interdict a target, and then we overlay with that known consequence. So there is going to be, if you make a bad decision, there's going to be collateral damage to that decision. So understanding when you make a decision, how does that impact, the overall process? So this is the experiment paradigm. So we have humans with physiological monitoring being shown a variety of clips, and I'll show you those clips, and asked when and where to make the interdiction decision based on this sometimes faulty information. All right, so there's two maps. You have a target localization shown here, and then in parallel, you have a risk map, so which tells you where are the likely targets of collateral damage. And so when you make a decision, even if you choose coordinate x, y, there's a probability that it's actually going to drift somewhere to the left or the right or up or down in time. So even if you make a decision to interdict here, there's a likelihood that you might actually hit here, so with some known probability. Yep?
So you mouse it in the wrong.
Sorry. Yep, it's not showing up. Is that better?
Yes.
Is that better? Can you guys see that? Okay. Thank you, sorry. So yeah, if you choose, this is your likely target, and you choose to interdict it, it may actually hit someplace nearby that has a known collateral damage. All right. Let's see if this will start. So there's 4 different levels of autonomy that we employed. The first is just showing you where a sensor, whether that's a human or a hard sensor, is giving you a target ID. Then we gradually add additional levels of autonomy to that, adding a particle filter with some kind of memory so that you can project where that target might move in space, adding some decision support that encourages you when to interdict based on lowest consequence, and see how the humans did. Come on. So what you can see initially is you see these circles so this red target up here is the actual target location. Obviously that didn't show up in the experiment, but for ease of demonstration. And what you can see is that gradually, as you increase the decision support, you start to see these particle filter heat maps start to show up around it. So initially it's just flashes of target, 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 and you have to make a decision. There's some false positive rate associated with each of these sensor sources. The sensor sources themselves are, come on. There we go. Sensor sources themselves are these hard fixed points. So you have a known sensor range associated with them. And then what you see across the bottom is this fire recommendation and the ultimate highest level of classification, assistance. All right. And I don't actually have the data there, so Ryan is preparing that data for publication. But what you see is that as you increase decision support, your collateral damage goes down substantially, and your correct interdiction goes up substantially. So, all right. So this is we're a semi-academic group, and so I wouldn't be, I'd be remiss if I didn't somehow tell you that we publish lots of things. So we publish lots of things. Yeah. So what I'd like to highlight is we have these large data collections going on that we would like to eventually publish so that other people can look at this data and tell us what we're missing or what are the solutions that we should be trying in this space. All right. This means I'm almost out of time. How much? Okay. So this falls into the next research. So as I mentioned, that last project is ending. We started a new project that is an internal big idea project, which means it's one of these big science questions, which is continuous multifaceted soldier characterization for adaptive technologies, which means just about nothing, but that's what the people all the way up the food chain decided this should be called. So this is soldier variability. So we are inherently all variable. In between each of us, we all have different capabilities, different, all things about us vary from person to person, but also within you in time. So your capabilities to answer that question on the exam today versus last week versus last month are very different. Today versus midnight tonight is going to be different. So how can we determine what your current state is? In order to do that well, we need a really, really, really big data set. So there's lots of theory that goes into this, and I'll get into this. But just like to highlight why we're doing this. Generally within the military, as also within industry writ large, you determine what are the capabilities, and then you design to the lowest common denominator. So the person that can just barely pass the test to enter a certain group, that you design for that person, which means you give up all the capability of all the rest of the people in that unit. So if you can actively determine what those capabilities are, you can substantially improve that unit performance without doing anything else. So in how you can change how you train them, you can change how you equip them, you can change how you do everything else, if you can just determine what their capabilities are over the spectrum. So that's the goal we're trying to get at. I won't go through all the details. There's two big thrusts. One of them is the math that goes behind it. What is the fundamental framework? And the other piece is the physical wearables. So in order to determine your capability, I need to be able to determine your capability, which means I need to be able to measure you. And our current wearable systems are pretty not so good. I'm trying to think of an appropriate way to put that, but they're not good. So if you take your Fitbit, the data you get off your Fitbit is pretty crap. So how do we make better state estimates with bad data? Or how do we make better sensors? And that's what the second part's. All right. And then we have this big, giant experiment that we're doing where we have hundreds, literally hundreds of humans, mostly ARL employees, that are willing to wear these physiological monitoring systems 24 hours a day, 7 days a week for 6 to 12 months. And we monitor them, and we monitor everything about their work environment. So this is a giant collaboration space. So like the atrium you have over in the EE building. So think of that with whiteboards and computer monitors, and everything about that system is mutable, meaning we can change and actuate every surface on that. So we can change everything about it and change the environment, the lighting, everything. And so there's going to be a giant data set, so we can actually start to understand human variability and its impact on productivity. So this is for an office environment. Next step is we take that to the training environment. So we have work going on in this for soldiers at West Point. So how do we work with them and the training centers down in Tampa? So how do we take this into training environment with the hope that if it works in the office and it works in training environment, then ... it should work in the real world where we worry about. All right, lots of sensors. I'm going to get to the end. We publish lots of stuff again. Sorry, it's an academic talk, I have to say that. Last thing, and then I'll get off the stage. So open campus, so this is I already mentioned. This is a spectrum where ARL does work. So all the way down here, this is the basic science, all the way up to supporting systems in the field. So we do a little bit of prognostics and diagnostics work. So when things break, we tell them why and where and how to fix it. But most of what we do is down here on the discovery and innovation end of things. So this is our workforce. So it's a very diverse workforce, about 3,000 folks, mostly PhDs, lots of masters and BS level folks working there across a variety of disciplines. These are the different application spaces we work in. So you'll have this information afterwards if you want to look at it, and I can point you to all the further information. But we do work across the full spectrum of stuff, not just novel sensors and humans in the loop. This is what, so we're actively looking to recruit new people to work with us on site, actually for us, or just with us. So if you have stuff you want to do with us in collaboration, we would love for you guys to come work with us. So our facilities are here. These are our primary facilities. So one right outside of DC, one between Baltimore and Philadelphia, and one in New Mexico, none of which are nearby to you guys. So that's a challenge. So what we did is we added a whole bunch of other sites. So we have a whole bunch of satellite sites that we've now added to the system. So we now have sites at UC Santa Barbara and at USC. We have a site standing up at Salt Lake. We have all these green dots, which are field elements, a whole bunch of other sites on other campuses. And then we added these new campuses to ARL. So ARL South is now in Playa Vista, California. ARL West is Playa Vista. ARL South is on UT Austin's campus. We have a new one standing up in ARL Central, which is on University of Illinois. This gives accessibility for you to come work with us and us to come work with you a lot easier than making you come to DC and work on our facility there, which is fully, we embrace that. But with that, there's all these other sites as well around the world. And the way we make that happen is putting these in place. So this is lawyers speak for getting all the IP issues out of the way. So we put these cooperative research agreements in place, and this is how we've enabled that. So we now have big cooperative agreements with big institutional systems like UT, University of California, all these big, University of Florida, all these big educational empires we now have giant umbrellas with. All right, and we also do a lot of work with industry, which is really cool. So we can instrument the NFL players and look at CTE issues. But I'll get off the stage with that, and I ask if you guys have any questions.
Great. We already had a lot of really provocative questions throughout the talk, but it looks like we might have a few more.
Yep.
Yeah, I guess it's like more of a philosophical debate than an actual question. But let's say there was like actually a fatality caused during like autonomous control. In that case, what do you think? Like, who's more responsible? Is it the person who wrote the code, or is the person who was supposed to chime in and like control it?
Yeah, that's a great question. Yeah. So the question was, in the case of when a fatality or an error is made when autonomy is in control, who's to blame, basically? And I think that's a fundamental question that we as a society are going to have to solve. So this is not the first time that we've had these big questions. And so we've solved this before. The one that comes to mind is how we dealt with the issue of vaccine development, which is a big society good, but there are known side effects to some of these. They may be very rare, but there are known side effects to some of the vaccines. So we put this big institutional neutral body in place that assesses the claims. And I think that we need something similar to that to enable autonomy integration, because there are going to be these issues. And we need to not let the courts decide on a state-by-state, county-by-county basis of who's responsible. So we need to put some kind of an umbrella agreement, and Congress stepped up and did that for vaccine issues. So perhaps this is a model that we could work with for autonomy issues. Yeah. All right.
Very interesting. Any other questions?
All right, so one last thing before I get off the stage then. So I think it's really awesome where I work, but so Popular Science agrees with us. So we're one of the most awesome labs, and those are my students up there that made that list. So it's fairly unbiased. opinion.
That's very cool. Yeah, and for those that aren't familiar, this is actually kind of a new policy of ARL to actually try to work more, have a more open campus and try to work more closely with universities. So it's really kind of an exciting time to try to develop these collaborations.
Yep.
So let's give Will one more round of applause.